Okay, so in this topic 2, this is rather long, but we're trying to do actually quite a bit here. We're trying to get actually an entire sub branch of the entire discipline of statistics done in one chapter. So, just as our review from topic 1, statistics is broken down into descriptive statistics and inferential statistics. I'll be honest, and there's no need to sugarcoat this. This chapter is not the reason why any of you are required to take this course. It's useful information, and you'll obviously be tested on it. But really, what we're trying to do here is we're just trying to structure how you actually would display data, describe the data in very simple numbers. The reason why it's not the reason why you're required to take this course is because it's the inferential statistics that is more useful both in the business world as well as for research purposes for those of you who are social science students. Here, we're just going to cover the material that would be needed if someone said, was to give you data and say, tell me what's going on in 30 seconds or less. And that would be kind of what you would do with descriptive statistics. Okay. So, as usual, the first question, and again, my apologies, to be organized here, I print out the PowerPoints, make some notes, and so here's some rustling of papers here as I proceed through this. The first thing that we're going to do here is we're going to talk about the 3 primary ways that we try to graphically display data. That would be with the stem and leaf diagrams, the frequency histograms, and then the relative frequency histograms. Then we're going to talk about different ways in which to talk about the center of the data set. That would be primarily things like the mean, the median, and the mode. Which I guess is right here. And then we're going to talk about the variability of the data set. How far do the rest of the measurements, how far are they away from that mean, median, and mode? What kind of variance do we have, and what's the standard deviation across that, across the measurements? And then we kind of finish up the rest of this topic by talking about not only the z-score, but then the quartiles for the distribution of the data, and then getting a box plot with a 5-number summary of the data set. All of this in descriptive statistics is designed to give us an overview of the data based on some just very simple measurements. Okay. So let's start with what is one way in which we could describe the data. One way that we can kind of rewrite the data that we have presented to us would be with a stem and leaf diagram. And what a stem and leaf diagram is designed to do is it's designed to, they should have given you the other, I see here what they're showing here. Okay, so here they're just showing you, I probably wouldn't have described it this way if I were making the slides, and again, I didn't make the slides. They're starting off by showing you what a stem and leaf diagram is, and you would look at this at first glance and be like, what the fuck is this? It doesn't make any sense. It's just a column of, it's multiple columns of numbers. What does that mean? Well, let's get to the rest of the slides here. Basically, we have on one side of that column line a tens place, and then in the rest we have the units. So that would be our stem and our leaf. So if we go over here, here's our stem, here's our leaves. So we'd have something that's 25. And then what we'd have here is something that's 40, 58, 69, 68, 69, 77, 73, and so on and so forth. But we have nothing with the 3 as a stem. We have no leaves with this stem here. And so, you know, for some individuals, this would be a useful way to describe the data. It gives you a pretty quick sense of how many you have for each of the tens variables. And again, we could then rearrange the leaves, and that's what's done here. We could rearrange the leaves and rearrange those leaves in numeric order. So then I would see that pretty quickly I have 2 that are 70, 70, and 70. Whereas if I went back over here, it's a little bit less clear because it'd be 1 of the 70s and then 2 of the 70s. So you can rearrange the leaves to make the understanding of the data, the display of the data, more useful, more descriptive for what you're doing. Okay. Now, besides the stem and leaf diagram, the other thing we could, just making sure here, sorry, one second. Sorry, let me make one last comment about stem and leaf diagrams. So why would you do it? I guess this is probably an important unanswered item here. The reason why we would use a stem and leaf diagram would be that we want to kind of quickly display the data's distribution across the range of the values. So basically, I could see that within the 20s, I've got 1 observation. Within the 30s, none. Within the 40s, I've got 1. Within the 50s, I've got 1. Within the 60s, I've got 3. And then we can see here, you know, if we're trying to see where are most of the observations, it's pretty quick. We can pretty quickly look at the stem and leaf diagram and see that it's on the upper tail of this data, the 70s, the 80s, and the 90s, where most of the data points are. And that we can do pretty easily with the stem and leaf diagram. So now we get to a second way of talking about how to display the data, and that would be the frequency histogram. So in a frequency histogram, what we're doing here is it's providing us a way to look at the data like we did with stem and leaf, but do it with a much larger data set. So you'd use stem and leaf for a smaller data set, frequency histogram for a larger display of the data. And basically what we do is we have, with our variables, we have an x-axis and a y-axis, where the x-axis we would look at the scores themselves, and then on the y-axis we'd look at how many observations, or what's the frequency in which that score occurs. And so if we look at this here, we're seeing that here we've got the relative scores. And so this is the exact same data as we saw with stem and leaf. So we're not trying to change anything here. We're just trying to redisplay the data as we have it. And you can see we can pretty quickly see, we can come to the same conclusion, that the data is skewed towards the 70s, 80s, and 90s in terms of number of observations. But here what we're doing is that all we're showing here is we're showing the stem. So we had 1 in the 20s, 1 in the 40s, 1 in the 50s. And I think if I remember correctly, 3 in the 60s. And that's what we're showing here. On the y-axis, we're just showing how many observations were in that stem of the 20s, how many observations were in that stem of the 30s, 40s, 50s, and so on. Now, you don't have to arrange the score with a stem like 10, 20, 30, 40, 50. You could do it within a range, anything you want. Really, again, what we're trying to do here is get a quick glance of what's going on with the frequency of the data. Now, interestingly, if you think about this, if we were to, I don't want to, why not? I'm not going to. Let's see here. You can kind of see, if you look at it this way, look at this. So with the stem and leaf diagram, you can kind of see the frequency distribution here as well, right? You can kind of see it here. Okay. And again, the frequency histogram is again just displaying the same data as the stem and leaf. And then with the third one, we're looking at the relative frequency histograms. And with the relative frequency histogram, what we're doing here is instead of looking at a count of how often something is occurring, we're looking at the relative frequency. So that would mean the frequency f, which is in the numerator, over the total sample size n. So let's just jump to how that looks. So that would kind of look like, in this case here, where we get a pretty good idea of how the data is distributed between A and B, where it all has to add up to 100% from one tail to the other. Now, what that does for us here is it allows us a way to the one thing that we would see is that within the 70s that we had the highest relative frequency, and then again in the 90s, and then in the 80s, which again, it would be, in this case here, we could add up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so just confirming we have 30 observations here. So then we'd have 1 over 30, 0 over 30, 1 over 30, 1 over 30, 3 over 30, and so on and so forth for our relative frequency distribution. Now, why would we do a relative, let's just, before we get into this here, why would we look at a relative frequency histogram? What it does is if we have a large enough sample size, you can see, that's why it's called a very fine relative frequency histogram, because if you have enough observations, you would see that this bell curve becomes much more smooth. And so we would see this when the data set becomes even larger. So you're getting a sense here that we proceeded through these three ways of describing the data, with the data set becoming larger and larger and larger, where the stem and leaf was a smaller data set, then the frequency histogram being a medium-sized data set, and then the relative frequency histogram being a much larger data set. And if you get it large enough, then your bell curve here becomes smoother. What you can get a sense here, though, as we transition to the next topic, though, is you get a sense of where the data is sent around, somewhere around here, right? It's kind of the center of the data. You can see that graphically that's occurring right here. The question would be is, what number is that? So that's what we turn to next. And probably the most common way of talking about the data would be with the mean or the average. And that most of you should be pretty familiar with what that is. So if we talk about here, we would say that the average is equal to summing up the total of all your measurements and dividing it by your number of observations. So that would be your n. So for instance, if I added up 4 scores and it added up to 100, then the average would be 25. Right, and that would be kind of simple, that the average, if there's 4 observations that total to 100, then the average would be 25. But as you kind of get a sense here with averages, it's not always that way. Things do deviate from each other meaningfully. So that would mean that as we take in, not jumping ahead here to the next section, but after we describe the center of the data, it'll be useful to describe how much things deviate from that center. What else do I want to say about this? So the only other thing I think we can say is that we can go from a sample to the population, where now the population is the population is the sample. So n is the population size. So the extent of this formula isn't the same. It's just that we're going from sample to population, where now we're saying that the mean of the population data is equal to the ratio of the sum of all the values in the population over the entire population size. The structure between these two variables, it obviously has a similar structure though. All we're changing though is going from sample to total. Okay. Okay, I'm going to pause here for a second. Okay, so, sorry, and just before we take away from the mean here. So, when we think about the mean, that should be kind of your go-to or your default description of the data. The larger the data set, the more accurate your mean will tend to be as a true measure of the center of the data. The smaller your sample size, the less useful a mean is, because you could have a score of 100, let's say your sample size is 2. You could have a score of 0 and 100, and your average is 50. And that is not very descriptive of the middle of your data by any means. So larger the sample size, better the mean is as the center of your data. Now, what you alternatively could turn to would be the median. So in looking at the median, typically what we're doing here is we're looking at the middle number. So we would basically rank order all of the observations. Let's say that we had 11 observations. And so then what we would do is that with those 11 observations, the median would be the 6th observation, because at the 6th observation, you have 5 measurements below it and 5 measurements above it. If you have an even number of measurements, simply what we would do is we would take the 2 middle measurements and take the average across those 2. Again, rank ordering the numbers in your sample. So, we can try to look at, if we look at, let's see here. So let's say that we've got So in this case, what would be the mean? The mean would be the sum divided by the number of observations. In this case, it would be 5 plus 7 plus 11 plus 21 plus 30 over 5. Let me get out my calculator here. And I'm just making up these numbers as I go along here. So that would be 74 divided by 5. So that would give us an average of 14.8 as a mean. Now the median would be 11. Basically the data organized from smallest to largest, middle observation. So you can see here we've got a mean of 14.8, a median of 11. And again, you're in some sense you want to tell your reader of your research everything possible about what your data looks like so that they can then make their own informed decisions about where things are at. Okay. Let's stop this. Let's try. Okay. So here we've got a display of data. We've got a different data set, 0, -1, 2, and 2. So then the first thing we need to do is we need to put it in order, smallest to largest. So -1, 0, 2, 2. So same data, just smallest to largest. The two middle pieces of data here would be 0 and 2. So we need to take the average of 0 and 2 and then divide it by 2. So 0 and 2 divided by 2 would be 1. So the median in this case would be 1. The average, if we were to add up all these scores, -1 plus 0 plus 2 plus 2, and then divide by 4, we would have 3 over 4, which is 0.75. So the mean would be 0.75. Again, I'm showing you that so that you get a sense that mean and median are useful for describing various aspects, various different ways of describing the same data, for us to get a sense of what's going on in terms of the center of the data. What else do I want to say here? I'm not sure why they're jumping ahead here to. Let me just draw something here. So the idea here is that, if I've got data that looks like this, the mean is going to be a pretty useful way to understand the data because it's kind of the halfway point of the arc of all the data points here. Where something like the median becomes more useful is if the data kind of looks a little different. Because then the idea is that maybe 50% of my observations are here, and 50% of my observations are here. Whereas here it's 50, 50. So do you see what's going on there? With top being the mean, bottom here being the median? Is that, sorry about that. I didn't realize it just gets rid of it. That kind of sucks. Sorry. Rewind the video and look at that. So I'm going to imagine in my mind. So just rewind the video a little bit just to get a sense of the data. But the idea here is that you would use the median if the shape of the frequency of the observations is what we would call bimodal, or it's just not a normal distribution across a single peak of the data, the center of the data. I just want to make sure here if I look at the... Sorry, you're hearing rustling of paper here. Sorry, and I want to look at one thing from the textbook here as I'm talking about this too. Give me 1 second here. Yeah, you see this on page... you see this best on page 27 of the book. Let's just try to look at that directly. One second here. So I can't say enough about how important maybe page 27 is. Does it give me pages? Oh man, you guys don't give me pages. Come on. Okay, well, let me show you where it is here. This is right here. So this is pretty useful. If we're looking at the relative frequency histograms and the data is distributed in this kind of bell-shaped way, then generally speaking, the mean and the median will be identical to each other. And that's what we see here with panel A, and we even see here with panel B, where 50% of the observations are on one side, 50% on the other. Where it becomes useful to have data about both the mean and the median is when the data is skewed. And it can be either skewed right or left. And so here you see in panel C that when the data is skewed right, that what we tend to see is that the mean score here is to the right of the median score. So basically in this case, if this were an exam, the low performers on the exam, the low performers on the exam have made it so that the sorry, I need to rephrase this. In panel C, you've got a lot of scores. Most of your frequency is on the lower end of the scale. So this would be an exam where a lot of students did poorly. And if that's the case, then the mean score in general will be to the right of the median. So this would be your mean score, this would be your median. On the other hand, when your data is skewed to the left, as it is here, then your mean score is here, and it's pulled to the left of your median score here. Again, if you're just trying to give simple statistics, a mean score, a median score, it's useful to give both of those scores, because then if you told me those two scores, and I see the difference between the two, it's going to give me a pretty good idea about how the data is distributed and whether it's skewed to the right or the left, based on what degree of difference exists between the mean and the median. So I'm not sure, there's no real page number here, but I would take a look at this because this is pretty useful for understanding what's going on in the data. Okay, let's go back to the slides. So the next part we get here is the mode. And with the mode, sorry, I'm just trying to get to where we are here in the slides after I move things here. So again, with the mode, what we're trying to do here is find the most frequently occurring value. So if we had this very simple data set, 0 appears most often in that data set, so 0 would be our mode. There's not a lot of, I don't tend to use the mode very often. Really what the mode just tells us is the highest point in the histogram. I'm not sure what that tells you. It's just the most common score, the most common point in your data set. Which again, if you're looking at a frequency distribution, that would mean it's your most, it's the highest point. For any data set that we're talking about, there is only one mean, there is only one median. But for modes, you could imagine that there could be multiple modes. If you've got, if we had another value here, which was also -1, then we would have 0 and -1 as our modes. So you could have multiple modes, but you can have only one mean and only one median. In a real-life data set, the mode becomes a little bit more useful. I don't use it very often, but the mode is a bit more useful because generally speaking, when we're looking at a sample, the value that has, the measurement that has the highest frequency oftentimes is the middle observation. Not always the case, but it often is. I just don't like the idea of dealing with how often something is as my reliant point. I, as a researcher myself, tend to use mean and median much more than mode, but there would be times when the mode is important. So if we look at the mean, median, and mode, it's just 3 different ways of talking about the center of the data. And it's basically based on the size of the data set itself that we get a good understanding of which one is appropriate and how the data itself is skewed or not, of which one is more relevant to use, mean, median, or mode. With this idea that there is this difference between the mean and the median, it then means that we need to talk about the range of the data. How far spread out is the data across the data points here? So the range would be our difference between our maximum value versus our smallest value measurement within the data set. So the range would be the max minus the min. What that does for us is it gives us a way to kind of understand in our mind how the data is distributed. And then what we can do is use that to then start to talk about the variance. So when we talk about the overall variability of the data, the range. So let's just go back here. The range of the data would be that if I had a sample which had values like such as this, all I would do here is take 77 minus 30, and I would see that the range of data, the difference in our data is 47 points of measurement, whatever our units are here. 47 units of measurement between the max and the min score. That the maximum is 77, the minimum is 30, and our range is the difference between those two. Gives us a good idea, based on the size of that range, how much variability we have. In general, if we have a pretty small range, then we're probably not going to have that much variability. And if we have a rather large range, as we do here, kind of quickly glancing at it, if we have a relatively large range, then we do have quite a bit of variability. And we do see that. We have a kind of a skewed tail in the 30s, and then one in the upper 60s, mid 70s. Again, making up that data, I didn't do anything too interesting there. Okay. Okay. What do I do here? I'm going to pause this again just because I want to make sure I have enough time as I'm making this video. Let me pause here for a second. Okay, so now when we turn to the variance, or the way in which the measurements deviate from the center of the data, what we start off with here is a discussion of the sample variance. And for the sample variance, we're looking at the sample data, the number of observations, which is n. And what we do is we actually we find the squared difference between each observation and the mean. Square that difference, summed, and divide it by the number of observations minus 1. Now, even though this second equation looks more complicated than this first equation, typically what we look at here is that it's essentially a shortcut formula. It wouldn't seem it, but it is. So again, what you're doing here is you're just substituting, again, each observation squared minus 1 over the number of observations, summing the observation squared, n minus 1. Now, the reason why we do this is to start to get to a sample standard deviation. Now, what this does for us is it helps us basically talk about, again, that distribution of the data, the way in which data deviates from the center. And essentially what the standard deviation tells us is a simple numeric way of understanding, again, that variance in the data. Now, in this class, I'm gonna avoid asking you questions where you have to compute things like this, but I want a general awareness from you of what this equation is intended to do. Now, from this, what we start to look at is the population variance and the population standard deviation, where the population variance is this is a lowercase d, our delta squared and our delta, which again is computed in a rather straightforward way, but again, this would be for the population as a whole. What do those, I guess just to go back here, just to make sure we see things properly here. What the standard deviation and the variance, both for the population and for the sample, what they basically do is they give us a single numeric answer to the question of how variable the data is. And it becomes, in some sense, it becomes useful because then you don't have to draw out an entire histogram or talk about the mean, median, and the mode. You can just provide a single number for the variance and the standard deviation. You'll have a pretty clear, pretty quick, rough understanding of how variable the data is. Okay. That then brings us to the next part in this course, or in this section, where we start to talk about percentiles and quartiles. So the idea here is that what percentiles do is they tell us the relative position of the data. And we're basically going to look at two things here, the percentile rank, and we're going to look at something known as the z-score to do this. And what we do is we start to use that data to, now that we have an idea of the distribution of the data, now we can, with percentiles and quartiles, identify where in the series of data where this observation is. So if we talk about the percentile, or the pth percentile, what we're saying here is that if we had a value within the data set, let's give it x. So given an observed value x in a data set, then x would be the pth percentile of the data if the percentage of the data that are less than or equal to x is p. So the number p would then essentially be the percentile rank of x. What happens is that as we typically take the percentiles that would split all the data into fourths, and we call that the quartiles, which is here. So, if we wanted to, let's go back here. If we wanted to graph that out, where we're looking at the frequency on the y-axis, let's say we have a normal distribution, then essentially we would have our middle of the data right here. And here you would see the 4 quartiles of the data, with each of the quartiles containing 25% of the observations. This would be the first quartile, the second quartile, the third quartile, and the fourth quartile. And what we do as we start to bring this all together, let's get out of this here. Because I think we'll start to see it here. Okay, so let's remember that chart I just drew here. Let's go back here to calculating the percentiles and quartiles. So if we look at 10 different GPAs, so the question is what percentile is the value 1.39 in this data set? And then asking what percentile is the value 3.33. So the first thing we need to do with this data is we need to order it from least to highest. And that's what's done here. In this case, with 10 GPAs, each of these would be in the a 10th percentile. And since 1.39 is the very first one, that would then place it at the 10th percentile. For 3.33, would be 1, 2, 3, 4, 5, 6, 7, 8th. So it's in the 8th. It's the 8th number in this 10 number set. So that places it at the 80th percentile. What does that mean? That basically means that 80% of the observations are less than or equal to 3.33. In the 10th percentile, presumably this is the first, but you would have 10% of observations less than or equal to 1.39. Now, as you start to bring the data together, and just kind of remembering that graph that I just drew, well, let's just redraw it here. Not straight, but you get the idea. So again, first quartile, second quartile, third quartile, and fourth quartile. So the idea here is that the second quartile is the median. So that would be right there. So our median is right here. Half of the observations less than it, half of the observations greater than it. Not the mean, but the median. So then the start of the first quartile from 0 to here. Then the start of the fourth quartile from the maximum score all the way down to the 75th percentile. Okay. It's got the book provides some different ways, and these slides talk about some various ways to find quartile 1, quartile 2, quartile 3. It's useful and it's accurate. It's not inaccurate. But it really only starts to become, it only becomes a bit more familiar once you do it more often. So hopefully, well, certainly before an exam or anything like that, you'll have some experience looking at how to calculate these kinds of things. But it really all starts with organizing the data from least value to highest valued, finding the median, and then looking at where we are left of that center point, or basically less than that center point, and then where we are greater than that center point, or to the right of that center point. And then essentially within each of those 50th percentiles on either side of the median, you're basically finding the median again of each of those sides. And once you add in the data about the quartiles, and we add to that the minimum value and the maximum value, we get an incredibly useful piece of data called the 5-number summary. And what the 5-number summary does for us is it gives us a quick glance of how things are. To draw this out, we could imagine a continuum where we have the minimum value all the way to the maximum value. And we can add to it the quartiles. So we'd have X min, X max, and then quartile 1, 2, and 3. But you can see here with that 5-number summary, you get again a pretty useful description of how much variation there is in the data. And then what we can finally do here is just find the length of this box, and that would be our interquartile range, taking the value from Q3, subtracting from Q1. So from this point to this point, that would be our interquartile range. Oh yeah, how did I do that? Okay, well, we'll let it do that. Okay. If we go back to the data we had looked at, essentially what we would do here again is organize the data from least value to highest valued with these 10 observations. Since 10 is an even number, we would take the average of the two middle observations, in this case 2.53 and 2.71. So 2.62 is now our median. And then we have a lower set of the data from 1.39 to 2.53. And then the upper set of the data from beyond this point, 2.71 to 4.0. And then we find the middle value of that, and that would be 1.9 and 3.3. So now we have an idea of our quartile 1. We know our quartile 2 because it's right here. Right? It was that middle number we found, or the average of the two, if it's an even number of observations. And then for quartile 3, got it right here. And so what we're asked to do is rework this here with some slightly different data. And so, let's see here. So we have 9 observations. This would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 4 and 4. So that puts our median at 2.71. And then for the lower 50% range, we need to find the median here. And for our upper 50% range, we need to find the median here. So what we're going to have to do is take the average here. Sorry. 2.12 plus 1.9 divided by 2. So that would be 2.01. And then over here, we would have 3.33 plus 3.71. Sorry, it's just really bad writing here. Divided by 2. And that gets me 3.52. Dude, oh my god, it's getting bigger and bigger. I'm not causing this. I don't know why it's doing that. Okay, so let's... .01 and 3.52. And 3.52. So highest observation here would be 4. Lowest observation is 1.76. I don't know, my computer's just really grumpy right now. So we'd be at 2.71, 2.01, and 3.52. Again, my apologies for how this is looking, but this is generally correct. So right there would be our 5-number summary of how variable the data is. And then they did the work for you right here. But that's good, because it looks much cleaner than what I just did. Oh, sorry, and I could have then solved the interquartile range as 1.51. And so instead of drawing out the way that I did it, the 5-number summary, it's always in this order. Least, quartile 1, mean, median, quartile 3, max value. And it's always in that order. Okay. And there's our box plot that I've already talked about. And then what that takes us to, as we kind of wrap up this subpart here, is we need to talk about the z-score. So what the z-score does is it allows us to compute the distance of an observation, to get the distance between that observation and the mean, and that z-score is going to tell us that number in units of the standard deviation. So essentially what we're doing here is taking the observation x, and then we are subtracting the mean score, and then we are dividing it then we're dividing it by the sample size. If it's not a sample size and it's the population, then this would essentially be our formula here. And so essentially what we can do then is that we compute, when we know the x, we can calculate the z-score, and we can basically solve for the unknown. Essentially, what we see with a z-score is that if the z-score is negative, then we know that the observation is below the mean score. If the z-score is 0, then we know we're exactly at the mean. And if the z-score is positive, then we know that we exceed the mean score. And that's kind of what we see here. It tells us, essentially, the number of standard deviations we are away from the mean. 1 standard deviation, 2 standard deviations, 3 standard deviations. And 1 standard deviation, 2 standard deviations, 3 standard deviations. Okay. So if we want to try to solve this, what we would do is, again, we would, if we want to find the z-score specifically for 1.9, then what we need to do is take our 1.9 value right here and subtract from that the mean score, which is it the same data? Yeah, it is the same data. That's our median score. I guess we didn't find the mean actually yet. Did we? Okay. So we can find the mean score by adding all these up and dividing by the number of observations, and it should equal 2.645. And then we need to find the standard deviation amount. So for that, for our equation for S, we've got that right here. The square root of S squared, essentially. For our variance. And if we subtract those two, we do get, we can get closer to getting our z-score. by taking our observation, subtracting the mean, dividing by our sample variance, and we can see that with a z-score of negative 0.85, we know we are to the left of the mean, and we're basically about a third of the way, because essentially we would be about right here, This slide's pretty important. So if we start to look at a relatively normal distribution, then generally speaking, about 68% of the data is going to be within one standard deviation. That would be plus or minus. So if we go back to here, we would say about 68% of the observations are from one standard deviation here and here. So together, that's about 68% of the observations. If we expand it out to two standard deviations, that's going to cover 95% of the observations. And then finally, at 3 standard deviations, when the data is normally distributed, that would be when we are then at 99.7% of the data is collected within that sample of 3 standard deviations plus or minus from the mean score. And that's essentially what you see here, and now in much nicer form than what I just drew out. Yes, I did look at all the slides. I guess sometimes I'm just talking about it in more detail than I need to. Okay, I'm going to pause here before we do the last part. Okay, so that brings us to talking a little bit further about the empirical rule and leading to the Chebyshev theorem. So with the empirical rule, it is pretty important, not pretty important, it is essential that the data be relatively normally distributed, meaning that we have a normal bell-shaped distribution of the data with respect to frequency. It does not work when the data is asymmetrically distributed, meaning that we have multiple peaks or it's skewed to the left or the right. So we need a normal distribution. And what the theorem tells us is that, again, essentially, you'd have about 3/4 of your data set being within 2 standard deviations, about 8/9 of your data being within 3 standard deviations of the mean, and then when we look at the endpoints, that would be then where we can look at the k standard deviations. The theorem itself really only tells us the least amount or the minimum amount of data that has to be within those standard deviation ranges from the mean, but it could be greater. And again, none of this works unless you've got a normal distribution. And so that's what you kind of see here. So again, this would be used when you have a, you would start to use this when you have your non-normal distribution. You can certainly use it for normal distribution, but it really only becomes useful when you have a non-normal distribution such as this. Okay. Just make sure got everything else. Yeah, we do. Okay, so that kind of wraps up at least the material for this rather long topic. And I'll follow this up with dealing with some more practice questions about the material in this topic.